Before diving into any more code, we need to get familiar with some key concepts and define some key terms like cross-entropy, sigmoid, gradient descent, and so on. If you already are familiar with the theory, feel free to skip this video. Otherwise, to begin understanding all of these concepts, and to get a broad sense of how classification works, I like to refer back to an example, where imagine we're a hospital, or imagine a hospital, which annually tests thousands of patients, and they tell you to create a predictive model that's able to accurately determine whether or not someone is likely to be diabetic or not. Given this previously labeled data, we can predict whether or not someone is likely to be diabetic based on their age, which traverses the x-axis, and their blood sugar levels, which traverse the y-axis. Clearly a trend can be seen, such that the higher the person's age and sugar levels, the more likely they are labeled diabetic, the more likely they will be in the negative region. That said, every red point was initially assigned a label of 0. The lower the person's age and sugar levels, the more likely they are to fall in the blue positive region. Accordingly, every point that's blue was initially given a label of 1. Intuitively, a person who's 30 years old with sugar levels of 4 millimoles per liter would be somewhere in the positive region and thus most likely healthy. So you and I can predict that they should be in class 1. However, unlike you and I, a computer can't just eyeball this data and make such a prediction. What's going to happen is it will start with a random model, which more often than not will incorrectly classify our data. But then, the model will be trained through some optimization algorithm. It will be trained through many iterations until it reaches parameter values that can classify our data considerably well. So, given this model, which was obtained from previously labeled data, that's the key theme here. We use previously labeled data. Everything here is labeled 1. Everything here is initially labeled 0. We use this labeled data to come up with a predictive model that classifies our data into 2 discrete categories. And using that model, we can now make predictions on newly inputted data which don't have a label, based on whether or not that point lies below the line or above it. In our case, our trained model can now effectively determine that this person belongs in class 1, such that they are most likely healthy. Now you may be asking, how does the computer know how to come up with this linear model? Going back to the initial random line, what it's going to do is calculate the errors associated with this model, and then readjusts the parameters of the model to minimize the error and properly classify the data points. We then stopped at the following question: how does it calculate the error? Well, we're going to need a continuous error function. We'll call it E. Looking at this diagram, clearly there are 2 misclassified points. We know the blue points need to be below the line and the red ones above. So what's going to happen is this error function is going to assign each misclassified point a big penalty. As for the correctly classified points, they're going to receive very small penalties. We'll have it such that the size of the points reflects the size of the penalty assigned to them. The misclassified points have the largest penalties, since they are misclassified, and what we'll do is detect these error variations and thus figure out in which direction we need to move the line the most. The total error then results from the sum of the penalties associated with each point. We'll safely assume that the total error is very high. So what we'll do is actually move the line in the direction with the most errors. We keep doing that until all error penalties are sufficiently small. We're minimizing the errors as we adjust the weights of our linear model to better classify the points, and thereby minimizing and decreasing our total error sum. Mathematically, how do we determine this error? Well, we use the formula associated with the cross-entropy function. To better illustrate this, let's take a look at the 2 following models. Just purely from eyeballing this, we know this model is better than this one as it properly places the blue points into one discrete class and the red points in another, whereas this line mixes the red and blue points up. They're not classified correctly. Now, linear models give their predictions in the form of probabilities, such that points with a label of 1 should be in the positive region of our model, and therefore should correspond to probabilities very close to 1, and points with a label of 0 ideally should be in the negative region of a model, and thus should correspond to probabilities very close to 0. In our case, I've color-coded the points with label 1 to be blue and points with label of 0 to be red. Our two models then make the following predictions. It follows that the best model gives the higher probabilities for the points that we know should be in the positive region, and the lowest probabilities to the points that we know should be in the negative. And we've already tested this person. They're labeled 1. They're blue, and thus they should be in the positive. But, according to our linear model, this point here is in the negative region since its probability was determined to be under 0.5. And anyone that's red, suppose we've tested all of them, and we know they're diabetic. Yet this linear model predicts that this point is 80% in the positive, 80% likely of being healthy, which is also wrong. Clearly this model better classifies our data since it assigns the higher likelihoods to the point we know should be in the positive and the lower probabilities to the points we know should be in the negative region. Furthermore, all of these probabilities correspond to the likeliness of something being in the positive region, of being blue. We can look at this from another perspective. Since probabilities add up to 1, the likeliness of the red points being red, being in the negative, is simply 1 minus the likelihood of it being blue. On the left-hand side, one of our red points, according to the linear model, is only 20% likely of being red, which again doesn't make any sense. We know this point is red, we already labeled it as such. But according to the model, it predicts that it's unlikely for this point to be red. However, the second diagram once again makes a lot more sense. All the red points are more likely to be red, all the blue points are more likely to be blue. Every point corresponds to its respective label. And now to compute the cross-entropy value, we take the summation of the logarithm of each probability. In doing so, we've proven our original hypothesis, such that the linear model, which better classifies our points, results in a low cross-entropy value and a small error value, and the model that incorrectly classifies its points has a large cross-entropy value. Fundamentally, all we've done is take the actual labels of each point and compared each label with the prediction made by the model. From that, we can determine the total error, such that this model would have a large error, but now what we do is we use gradient descent to minimize that error and obtain a better linear model which better classifies our data, and it keeps doing that over and over through many iterations. It keeps updating the weight and bias values of the model in the direction of the least error until we obtain a line with optimal parameters. In the linear regression part of this course, we've already very briefly covered the math behind gradient descent and how it goes about updating the weight and bias values with respect to the gradient of the error function, so we're not going to go through that again. As you've already seen, it is very easily done in PyTorch. And that being said, once we've trained a linear model, we can use its parameters to now make accurate predictions. You know that the equation of a line is y is equal to mx plus b, where m is the slope and b is the y-intercept. The following model was trained to have parameters of negative 0.05 for the slope and 12 for the y-intercept for the bias. These are the parameters which, upon training, were determined to provide a line that best classifies the data. We will place this model inside of a node. We will refer to the y term, the blood glucose levels, as x2, and bring it over to the other side. We will further construct the perceptron by setting x1 and x2 as input nodes, x1 representing the age of a person, and x2 their glucose levels. Based on the model's linear equation, x1 is multiplied by a weight 1, x2 is multiplied by a weight 2, and the number 1 is multiplied by a bias value of 12. Alright, now suppose we wanted to test a patient with an age of 30, x1 equaling 30, and blood sugar levels of 3 millimoles per liter, such that x2 is equal to 3. Each input is multiplied by its respective weight, and by taking the linear combination, it yields the following value. We now convert this numeric value to a probability by passing it through an activation function known as the sigmoid function, which has the following equation, 1 over 1 plus e to the negative x, resulting in a value of 0.99. This person is 99% likely to fall in the positive region, which makes sense since if you were to plot this point with x1 equaling 30 and x2 equaling 3, you can clearly see that this would be indeed in the positive region. This is perfect. Based on previously labeled data, we used gradient descent to update the parameters of a linear model, to update the weights and bias values, until we obtained a model which accurately classifies our data points. And now from this model, we can now make predictions on newly inputted data which don't have a label, and the structure you see in front of you is known as the perceptron, which for concision can be redrawn as such. It is the most basic form of a neural network, as it only contains one input layer and one output layer, no hidden layers in between. Let's take a break and begin coding this perceptron-based network in the next video.